Okay, if f is Cauchy integrable, then g agrees with f except at finitely many points, so that g is Cauchy integrable. So if you set up, not only is it Cauchy integrable, but the two integrals are going to be the same. So you set up sums for g, Cauchy sums. You're not allowed to write down the integral existing for g because you don't know that. That's what you're trying to prove. But you can write down the integral for the Cauchy integral for f. Now, if you write down sums for g, they're going to be real close to sums for f because f and g differ only finitely many points. And you can always partition things so that the contribution, the subinterval that contains the points upon which they differ has arbitrarily small length. That's what you want to get to eventually. The subintervals where the two functions differ in total has arbitrarily small length. What's that allow you to say? That a sum for the f function and a sum for the g function are arbitrarily close. And of course, the sums for the f function converge to the Cauchy integral for f. And that should be enough to get convergence for the g integral to the same number. Right? That's the strategy behind that. But it's a good exercise in epsilons and deltas, deciding what to do, how to prove that. So you can't write down the Cauchy integral of g, you don't know that exists, but you can always write down a sum induced by some partition for g, and then show that since g and f are pretty close, those sums have to be pretty close, and if they are pretty close, then since the sums for f converge to the integral, the ones for g must as well. I mean, that's the argument.